In today's video, we are going to be taking a deeper dive into the Stefan-Maxwell equations and why are they important and useful. So Stefan-Maxwell equations are very important, especially in the field of chemical engineering, because they allow us to look at multi-component systems and perform binary tests to see how each different component interacts with each other and then how they interact all together. So if we had a mixture of, let's say, 5 different species or components, we would perform a binary test on 2 of them to see how those 2 components interact with each other. We could then do different tests on different components to see how those interact with each other. And then depending on the number of components you have, after you have completed your test, you can evaluate and see how they all interact with one another. This is very useful because if we were to perform one test on all 5 at the same time, it would be very difficult and very challenging. So performing these binary tests, so in groups of 2, it allows us to take an easier approach at seeing how these species interact with each other. Okay, so here I have written out a basic Stefan-Maxwell equation. So you'll see that we have numerous different variables in here. So I kind of want to go through and talk about what each of those variables mean. So you'll see we have 3 x terms. We have an x sub I, x sub I, and x sub j. So those I and j's are just dependent on whichever species we're looking at. So to kind of simplify this, I'm just going to have x sub a. And x sub a represents the mole fraction of, in this case, component A. Then you'll see we have this kind of upside down triangle and then a mu I. This upside down triangle will always tell us that there is a gradient. And then our mu sub I term represents the chemical potential. So putting those together, this is the gradient of chemical potential. And anytime you see a gradient like that in an equation, that will always tell you that that is your driving force. So moving on, we have this capital D sub ij. This represents our diffusive constant. And this just tells us how species I diffuses into species J. Then we have this C term that represents our overall concentration. And this is in units of molar. And then we have this capital N sub J and capital N sub I. And just like for A, I'm going to make this simple and put N sub A. And this N sub A is the molar flux of component A. And then, of course, you have R, your gas constant, and T, your temperature. So now this is kind of our base Stefan-Maxwell equation, and we can see how that relates to another Stefan-Maxwell equation that uses component velocities and their mole fractions. So we can write that out and see how that relates to our Stefan-Maxwell equation using component velocities and their mole fraction, and how we can express that using molar fluxes and diffusive molar fluxes. Okay, so now I want to simplify our base Stefan-Maxwell equation. So as I said before, the left side of this equation contains our driving force of species I. So I'm going to make this dI for the driving force of species I, and this is equal to the sum from j equals 1 to some n of the mole fraction of component I multiplied by the molar flux of component J minus the mole fraction of component J multiplied by the molar flux of component I divided by the overall concentration C and the diffusive constant of I and J. Now, normally when we're talking about components here, we're going to be talking about the vapor phase. Well, if you've taken any sort of thermodynamics course, you'll notice that when we're speaking about mole fraction, if we're talking about the liquid phase, that's usually when we use X. We use Y when we're talking about the vapor phase. So I'm going to simply change these X's into Y's, just so that we can note that we are talking about the vapor phase. Now I want to write out our other Stefan-Maxwell equation that relates component velocities. So this once again has our driving force of component I on the left side, and this is equal to the summation from J equals 1 to some n of the mole fraction of component I multiplied by the mole fraction of component J multiplied by the velocity of component J minus the velocity of component I, all divided by the diffusive constant of I and J. Now, the main difference you'll notice between these two equations, because once again, we're trying to relate them. So the main difference we can see here is that our second equation right here does not contain this overall concentration, C. So in order to fix that, we are going to multiply that overall concentration in the numerator and denominator. So we're going to have the driving force of component I is equal to our summation from J equals 1 to N of our overall concentration multiplied by the mole fraction of component I multiplied by the mole fraction of component J multiplied by the velocity of component J minus the velocity of component I divided by the overall concentration C and the diffusive constant of I and J. One thing I want to point out is that when you multiply an overall concentration by a mole fraction, let's say, of component I, this gets you the concentration of component I. And the same thing applies for component J as well. So if you multiply the overall concentration by the mole fraction of component J, you get the overall concentration of component J. So knowing that, we are going to incorporate this logic into our equation. So we're going to have the driving force of species I, which is equal to the summation from J equals 1 to N of the mole fraction of component I multiplied by the concentration of component J multiplied by the velocity of component J minus the mole fraction of component J multiplied by the concentration of component I multiplied by the velocity of component I. And this is all divided by our overall molar concentration C and our diffusive constant of components I and J. So we want to take our Stefan-Maxwell equation for velocity components and relate it to molar flux. So if you recall, molar flux of component I is a flow. So when we think of flow, we can think of velocity. So it's equal to the velocity of component I, and these are moles that are flowing through. So we need a molar concentration. So we multiply this by our molar concentration of species I. And the same thing can be said for component J. It's going to be the velocity of component J multiplied by the molar concentration of component J. And conveniently, we have both of these terms in our equation. So we can now plug in for the molar flux of I and the molar flux of J. So we're going to have the driving force of component I is equal to our summation from J equals 1 to N of the mole fraction of component I multiplied by the molar flux of component J minus the mole fraction of component J multiplied by the molar flux of component I. And this is all divided by the overall molar concentration and the molar diffusive, the diffusive constant of I through J. And look at that. This equation that we just derived here is the same as our equation up here. So perfect. We related our Stefan-Maxwell equation using velocity components to our Stefan-Maxwell equation using molar fluxes. But what if we want to now relate this to molar diffusive flux? Well, if you remember from before, molar diffusive flux is this capital J sub, let's say I, if we're talking about component I. And this relates to molar flux. So the molar flux of component I was equal to the molar diffusive flux of component I plus the mole fraction of I multiplied by the total molar flux, N. And we want to relate this back to a concentration if we want to start thinking about moles. So we're going to multiply this by our overall concentration. The same thing can be said for component J. The molar flux of component J is equal to the molar diffusive flux of component J plus the mole fraction of component J multiplied by the total molar flux multiplied by, excuse me, the overall concentration. So now we can plug this back into our equation. So we have the mole fraction of component I multiplied by the molar diffusive flux of J plus the mole fraction of J times the total molar flux multiplied by the overall molar concentration minus the mole fraction of J multiplied by the molar diffusive flux of I plus the mole fraction of I times the total molar flux N and the overall molar concentration C. And this is all divided by our total molar concentration C and our diffusive constant of I through J. So now we can simply start to distribute and simplify this. So this is going to be mole fraction of I times molar diffusive flux of J plus mole fraction of I times mole fraction of J times total molar flux N times total molar concentration C minus mole fraction of J times the molar diffusive flux of I minus mole fraction of J, mole fraction of I times the total molar flux N and the total molar concentration C divided by overall molar concentration and the diffusive constant of I through J. And you will see that conveniently these two terms cancel, and we are now left with the driving force of component I is equal to our summation from J equals 1 to N of the mole fraction of component I times the molar diffusive flux of component J minus the mole fraction of component J multiplied by the molar diffusive flux of component I divided by the overall molar concentration and the diffusive constant of I through J. And there you go. We just now related our Stefan-Maxwell equation using component velocities to our Stefan-Maxwell equation using molar diffusive fluxes. So now we're going to take a look at ideal mixtures, and we're going to say that in this scenario, the chemical potential that we are given is the chemical potential at a pure state. So the chemical potential we're given, U sub I, is equal to the chemical potential at standard state. Now we know that this isn't necessarily true. This is more so your ideal case. So what we're going to have to do is account for the fact that these two likely aren't the same. So on the right side of our equation, we're going to have to add our gas constant R multiplied by our temperature T multiplied by the natural log of the mole fraction of component I. And we have this gradient of our chemical potential, and that gradient tells us that this is going to be a change in chemical potential over a position. So this is going to be the gradient of our chemical potential, and that is equal to the derivative of our chemical potential, or a change in chemical potential over position. I'm going to say this is position Z. Now we can plug in our value that we just found for our chemical potential. So our gradient of our chemical potential is equal to the derivative of the chemical potential at standard state plus our gas constant R multiplied by T multiplied by the natural log of the mole fraction of component I. And this is with respect to our position Z. Now we can take the derivative of this, and we don't have to worry about our chemical potential at standard state because that's a constant, so that will go to 0 when we take the derivative. So this derivative becomes our gas constant R multiplied by T multiplied by 1 over our mole fraction of component I. And this is the derivative of the mole fraction of component I with respect to our position Z. Now we can take what we just solved for the gradient of our chemical potential and plug this back into our original equation. So we're going to have that the mole fraction of component I multiplied by our gas constant R times T, our temperature, multiplied by 1 over the mole fraction of component I. And this is the derivative of the mole fraction of component I with respect to our position Z. And this is all divided still by our gas constant R and our temperature T. And once again, this is still equal to the entire right side of our equation. So as you can see here, our mole fraction of component I terms cancel, as well as our gas constant and our temperature. Therefore, on the left side of our equation, we're going to have that the derivative of the mole fraction of component I with respect to our position Z is equal to, once again, this entire right side of our equation. So this is now our relationship between the chemical potential given and the chemical potential at a pure state. And this is good because this tells us that our driving force, this guy right here, is not being impacted from any other outside variable. It's only this concentration gradient or this derivative of the mole fraction of component I with respect to Z. And that is great. Okay, so now I'm going to take our equation that we just derived here for our ideal binary mixture and show how this simplifies back into Fick's law. So to do that, I'm going to change this to be in terms of molar diffusive fluxes. So I'm going to grab our equation that we have here for our Maxwell-Stefan equation that relates back to molar diffusive fluxes. And for this scenario, we are going to set I equal to 1, and our summation is going to go from j is equal to 2. Therefore, we need to include both our I equals 1, j equals 1 term and our I equals 1, j equals 2 term. So we're going to have the driving force of component 1 is equal to the mole fraction of component 1 multiplied by the molar diffusive flux of component 1 minus the mole fraction of component 1 times the molar diffusive flux of component 1 divided by our overall molar concentration and our diffusive constant of components 1 through 1. We are going to add on our term where I is still equal to 1, and this time j is equal to 2. So we're going to have the mole fraction of component 1 multiplied by the molar diffusive flux of component 2 minus the mole fraction of component 2 times the molar diffusive flux of component 1 divided by our total molar concentration and our diffusive constant of components 1 through 2. Now you can see that this term cancels, and that is perfectly fine because, again, this is a binary mixture, so there would be no sort of change in molar diffusive flux in that scenario. So we're going to have the driving force of component 1 is simply equal to the mole fraction of component 1 times the molar diffusive flux of component 2 minus the mole fraction of component 2 multiplied by the molar diffusive flux of component 1 divided by the overall molar concentration and the diffusive constant of components 1 through 2. Once again, we solved for this driving force right up here. So I'm going to bring that down. That was the derivative. And in this case, I'm going to make this in terms of y, just because, again, we want to talk about things in the vapor phase, and I want to stay consistent with our equation right here. So I'm going to have this as the derivative of the mole fraction of component 1 with respect to our position z is equal to, once again, our right side of our equation. And if we think about a binary mixture, we know that the mole fraction of those two components equal 1. So the sum of y1 and y2, our mole fractions of components 1 and 2, is equal to 1. So if we solve for y2, the mole fraction of component 2, that is equal to 1 minus the mole fraction of component 1. The same sort of idea goes for molar diffusive fluxes. If we have an ideal mixture at steady state, there's not going to be any net molar diffusive flux. So that is going to be the molar diffusive flux of component 1 plus the molar diffusive flux of component 2 is equal to 0. And if we solve for the molar diffusive flux of component 2, that is simply negative the molar diffusive flux of component 1. So if we plug those back into our equation, we're still going to have the derivative of the mole fraction of component 1 with respect to our position z. And this is equal to our mole fraction of component 1 multiplied by the negative molar diffusive flux of component 1 minus 1 minus the mole fraction of component 1 multiplied by the molar diffusive flux of component 1, still divided by the overall molar concentration and the diffusive constant of components 1 through 2. Now we can simplify out our equation if we start to distribute in. This is going to be negative the mole fraction of component 1 multiplied by the molar diffusive flux of component 1 minus the molar diffusive flux of component 1 plus the mole fraction of component 1 multiplied by the molar diffusive flux of component 1 divided by our overall molar concentration and our diffusive constant of components 1 through 2. These two terms conveniently cancel, which is perfect, because this becomes the derivative of the mole fraction of component 1 with respect to our position, and that is equal to negative the molar diffusive flux of component 1 divided by our overall molar concentration and our diffusive constant of components 1 through 2. And this is Fick's law. It might not look like it, so we are going to rearrange. We are going to have the molar diffusive flux of component 1, which is equal to negative the overall molar concentration multiplied by the diffusive constant of components 1 through 2 multiplied by our derivative of the mole fraction of 1 with respect to our position z. And this is Fick's law. So we just found out how we were able to simplify our Stefan-Maxwell equation to Fick's law, and this kind of works out perfectly because you might notice that Fick's law kind of has some sort of limitations on it, so it has to be in this kind of ideal scenario, this ideal binary mixture, in order to simplify down to Fick's law. That's kind of its limitation.